Okay, I think I'm live. Welcome, guys, and glad to have you here. If you're looking at this video, I just wanted to do an example of a hydrostatic force problem, and I'm going to steal one from our book. Before I do that, I want to really quickly go over the units and what hydrostatic force is, or pressure, more likely. Force is force. It's still whatever it was. What's force? Mass times acceleration. Okay? And the book goes over that, but we're going to dwindle it down here a little bit. For us, especially when we're talking about hydrostatic force, we're going to talk about pressure. And what pressure is the it's the force per square meter put upon something. So force per square meter. That's what pressure is. And so when we're talking about this, let's say we wanted a pressure of the bottom of a glass of water, and there's water in there. Well, we would know the depth of the water. We would need to know what gravity is, and we need to know the density of water. And so, and this would be the force, and then this is the depth, and that gives us the pressure sorry. I guess the whole thing would be our force in this case. Oh man, now I'm just tumbling over myself. Hold on, we'll get this. In any case, pressure, it will be our if we solve for this, all right, I'm just gonna go here. Pressure is actually force over area. So again, it is your force per square meter. That's on it. Okay. And so in this case, we're getting our pressure here. Yes, this will get us our pressure. Force now here, if, like I said, take this and solve for F. Force is pressure times area, and this is mostly what we're going to use to set up integrals. And I just want to show you this as an alternate method to solving these hydrostatic force problems to the other videos that we have. So if we work all these out, we got kilograms per meter squared, meters per second squared, and meters. What do you get? You get newtons per meter squared, which is our work. No. Anyway, it's our force per meter squared. Anyway, or we call those pascals. Pressure could also be if we just have weight density, right? So this would be for good old metric units. Now for American units, we got we'll have a weight density, and for water, it's 62.5 pounds per foot cubed, and times depth. And again, we're going to get, you know, a force pounds times our per square foot. And so in any case, we have pressure. And when we want the actual force put upon something, we're going to need force is pressure times area. So without further ado, let's add a page and let's get a problem to work on. Okay? So I thought I had a problem ready. Give me 1 second and we shall have one. Okay, sorry about that. I lost my place. And now I have it. Okay. Let me go ahead and I'll snip this for you guys and get us a problem to look at. There we go. Okay, and there it is. So a dam has the shape of a trapezoid shown in figure 2. And I guess I could go ahead and snip that too, save myself some time and save you guys from seeing my terrible drawings. They're not that terrible. They're not great. Here we go. Okay. So this would be our picture that I want to make bigger. Because the bigger the better. Oh, a nice big picture to work with. Okay. The height is 20 meters. The width is 50 at the top and 30 at the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So one more time. A dam has the shape of a trapezoid. So you imagine a dam and there's water in the dam, and this is just one edge of the dam, right? The height is 20 meters. The width is 50 meters. The top is 30 meters at the bottom. I'm sorry. It's 50 meters at the top, 30 meters at the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top. Well, like with any of these, what we want to do is find an approximating rectangle, a little chunk to start looking at. In this case, I'm going to take a look at, let's say, here's my little chunk. Oh, and it's hiding. Hold on. Send it back. There. Got it. Okay. Okay, so here's my little chunk. And so, what is this? This is ridiculous. Hold on. There. There. I am still learning how to use OneNote, and it is sometimes a little annoying. In any case, move to back. There. Good enough. Let's say that's it. Okay. Now, so the pressure here is much more than the pressure on the dam at the top because there's less depth. That D was for depth, right back here. This D is depth in meters. Maybe I didn't make that clear. Okay? Depth in meters. Same thing right here, depth in meters. And so the pressure here is not as much as the pressure at the very bottom, way more pressure. And you can think about that. There's way more volume. There's way more water up there to push against it here. And the thing with hydrostatic pressure is it's the same in all directions. So no matter where you are in the water, the pressure right above you, right below you, left and right, it's all the same. It's all pushing against you. And so if we're looking at this, a rectangle like this will approximate the pressure at some depth. In this case, let's say our depth is x sub I. Let's say this is 0. So we'll say x equals 0 here. And we'll say here x equals Well, actually, maybe not. Maybe I want to put my x equals 0 a little bit, yeah, a little bit below. I think that is what I want to do. I don't want x equals 0 right there. Oops. Let's put x equals 0 right here. Because obviously there's no pressure being put on the dam up here. There's no water. There's no hydrostatic pressure. So let's say we're starting here at 0 depth. So that means right here would be -4 for depth. And x sub I is x for our depth. And so that would make this. We're going from pretty much it's 20 minus 4. This would be 16 for depth. There we go. Okay, so label that picture, right? And let's call this little rectangle here that we need to find the pressure on that little rectangle. And then, of course, the strategy is move that rectangle around and approximate the total hydrostatic force on the wall, on the dam. And then if we made those rectangles smaller and had an infinite number of them, well, then we got our integral. So we're going to add up the force of each of these guys. So we'll say force sub I. And going back here, well, force again was pressure times area. So what we're going to need is the pressure of each of these guys times the area of each of these guys. The pressure, that's easy. So P sub I think we can figure out right now. Let's go ahead and do that. P sub I is, we're in metric, so it's going to be, we can go back and take a look if we need to. Rho times gravity times depth. So 1,000 times 9.8 times depth. So it's 1,000 times 9.8 times our depth, which in this case is x sub I. That's fine. Next, we got to find our area of these rectangles. Well, the area, at least I know one dimension really, really easily right here. That is obviously delta x. So we got delta x here. The hard part is this. What is this distance here? Well, okay, if I'm looking at this, hold on one second. If I'm looking at this length, well, I guess what I would do is kind of break it up like this. Like, okay, well, it's going to be 30, because this right here is always there. It's 30 plus 2 times whatever this length is right here and right here. And that's the hard part. So really, this kind of problem, the hardest part, a lot like with the work problems, some of them anyway, is just the algebra and just figuring out these little things. I'm going to copy this picture down a little bit here and try to get a formula for this, right, with respect to x. Like, what is this distance with respect to x? And I like to use approximating rectangles. Well, I know that's 50, that's 30. We can say this is 10, and this is 10. Just these little pieces here. 10, 10. Whereas 50 is, 50 is the whole thing. That whole thing is 50. But 10 plus 10, so 30 plus 10 plus 10, 50. Okay, great. So I know this is 10. And then I got an x value here, x sub I, which is actually my x sub I, so let's say if this was 5, well, that's 5 from here. So the actual distance is going to be x sub I plus 4. So if I'm looking at the actual distance from here to here, it's x sub I plus 4. Or actually, I don't think that's the distance I want. I actually want this whole thing. So I'm going to have, if this is x sub I plus 4, then this part is, well, what's the whole thing? The whole thing is 20, so that's going to be 20 minus x sub I plus 4. That's going to be that piece. And then we got our unknown, our little unknown length here. So I don't know, let's call this, I don't know, let's call this y sub I. Why not? I don't care. Let's call it y. So we're trying to figure that out. So we have similar triangles here. I can easily find what y sub I is in relation to x, which is what I want. We're doing all this stuff in x. So let's write it out now. Now we got, well, the whole thing before was 20. So that's easy. So I got 20 over 10 is equal to this piece, which is 20 minus x sub I minus 4 over y sub I. And while I'm at it, let's make a note here. This is really 16 minus x sub I. Okay, so we're getting there. This is super duper the hard part. We're almost there. Cross multiply, and we got 20 y sub I is equal to 10 times 16 minus x sub I. And then we'll divide both sides by 20. Divide by 20. Divide by 20. Oops. 20. And we get y sub I is, let's just say 1/2 16 minus x sub I. Beautiful. And so, and I love the 1/2 actually, because remember what we said, our distance is actually going to be 30 plus 2 of these. That's our distance. That's what needs to go here. So we're going to write 30 plus 2, and it looks like we need a little bit more space. So let's get rid of this delta x for now. 30 plus 2, oh, 2 times 1/2, well, that's just going to cancel out. So 30 plus, redo. Okay, 30 plus, here we go. 2 times 16 minus x sub I. Well, let's just say 30 plus 16 minus x sub I. And it's all that times delta x. There's our area. And remember, our force, our approximating force was this. So if I just want to take this times this, stick it in an integral, now we have our integral. And I will just do that. I'm going to do it right here. I'm going to say, you know what? Take the limit. So I don't know. Actually, we'll take it easy. So let's say force is going to be about the sum of, well, pi times ai. So what we got is, I don't know, 9,800. X sub I times, what's this? 46 minus x sub I. delta x. And if we took that, well, let's say we had n number of triangles. We had 1 to n. For I, we had n of those triangles. This would get us about the force, but if we wanted to equal the force, let n approach infinity, and that would get us our integral, which is going to be 9800 x times 46 minus x dx. Okay? Now, so I wanted to show you guys this because some of you would find this method much better than trying to memorize keep doing that. Excuse me for a second. Anyway, would much rather use this method than memorize formulas, because this is very similar to work. You just have to remember, oh, okay, I'm finding the pressure, which is pretty much, it's the depth times the density times gravity times, and that's our pressure. So you just need pressure times the area, and that's the trick. And once you know that, you're good to go. There we are. Okay, perfect. And for us, the only other thing here I did forget to mention is, what are the limits of integration? Well, that's why the picture is so important. You guys see me there, draw and all, label this thing to death. We're going from x equals 0 to 16. And so I'm going from 0 to 16. That would be my limits. And this guy would be what we solve. And this would be a fairly straightforward integral to do. If you were going to do this integral, I would go ahead and maybe take the 9800 out. I'm going to finish it up. And it's going to be 9800 times the integral. And then we could distribute this x in here. 46x minus x squared dx. And then we'd, again, 0 to 16, 9800, and then integrate, and you can't get much better than that. 46x squared over 2, what is that? 23x squared? So I get 23x squared minus x cubed over 3. Evaluated from 0 to 16, plug and chug, work that out, and we get 4.43 times 10 to the 7th newtons. Whoops. Newtons. There we go. That's about what you should get. So there you go. Hope this was helpful. Let me zoom out here so we can actually see all the work on one page here. And any other problem is very, very similar to that. The hardest part, I really think, is once you got force, pressure times area. What's the pressure of an approximating rectangle times area of an approximating rectangle? All right, got an infinite number of those. The hardest part is figuring out some part of this triangle. In this case, it was the length of our triangle. It was very hard because we had to figure this stuff out, do this little side work right here. That was a tricky part. And you'll find that's hopefully where you guys have the hardest time, and everything else is easy. Because really the calculus, I think, is probably the easiest part of these. It's figuring out the algebra. All right, have a great day, guys. I'm going to end the stream. Here I go. I'm going to hit end the stream. And I'm going to repeat that because sometimes I don't know when the stream actually ends on this button that I press in YouTube. So here we go. End stream.